So from our last video where we explored two different scenarios where we were standing on the Earth measuring the effects of a rocket ship moving away from us, and the other one where we're on the rocket ship and watching the effects as we see the celestial bodies moving relative to us. And from those two situations we got these two equations here, and in both situations they both agreed on their relative velocity, and that's the only thing that they could agree on in those situations. And as we've already shown, time can change in each situation, the time experienced. So if that's the case, for speed to equal distance over time, if the times are different, the lengths must be different, which means we must have an equation, a mathematical equation, for how we relate the two different lengths. Now we already have an equation for time, and that's this: t equals t naught divided by the square root of 1 minus v squared on c squared. Okay, so if we sort of rewrite that, we can write, let's get t naught on its own. T naught equals t times the denominator. That's going to become useful to us in a second. So we can actually equate these two fractions to each other. And these are the two situations. So since they both equal the same velocity, we can put these two fractions as equal to each other. So if we rearrange this equation to get L naught on its own, or actually let's go L, that's the relativistic length. So let's get an equation, let's rearrange to get L on its own. So we've got this equation here. The wonderful thing is we already know what t naught is, so we can substitute that in. So let's take this over here and start a brand new section of our board. So we've got L equals L naught, and we're going to times it by t naught, which is equal to all of this. T and remember it's divided by t, and you can see here that this here, it's all times, this is on the outside, so we can get rid of t, and let's write what's remaining. L, which is the relativistic length, equals the proper length times the square root of 1 minus v squared on c squared. And this is our equation for length contraction. Our proper length is being multiplied by some number. Remember, this situation here, this thing here, is just a number. Now, if v is less than c, then this fraction here is less than 1, and you're taking away something less than 1. So this number here is a number between 0 and 1. So let's call it x. And it's somewhere between 0 and 1. In other words, you're making the length smaller. And so what we're doing here is we're finding that the length is being contracted, the relativistic length.